This is the unfortunate tale of Patrick the Frog, based on a tragic true story so eloquently commemorated in the heart-wrenching novel Touching Hearts by Dennis Hickey.
Who's that?
Hey there, kids. They call me Dr. A. Do you guys want to try some drugs? I've got some grade A isoproterenol, some caffeine, and some really potent potassium.
Oh, God.
I don't know.
What are you, a bunch of tadpoles? Try it.
Well, when you put it like that, let me try some of that isoproterenol. Oh, God! Woo! I think my heart rate might be increasing. Well, young Pat, isoproterenol is an interesting drug. Let's take a look at how it works. Sodium flowing through IF channels is the major ion behind the depolarization to threshold, corresponding to phase 4 of the pacemaker action potential. At a certain point, when depolarization is sufficient to reach the critical threshold, a cardiac action potential will be elicited. Calcium will flow into and depolarize the cell through long-lasting type calcium channels, or LTCC. This depolarization corresponds to the sharp rising phase on the autorhythmic action potential graph, or phase 0. At the peak of the action potential, slower time-dependent potassium channels have opened, and LTCC channels stop letting calcium in, corresponding to phase 2. The efflux of potassium ions results in cellular repolarization and the descending portion of the pacemaker action potential. When the membrane potential is again negative, the cycle repeats itself. Changes in heart rate, aka chronotropic effects, are associated with nodal cells. Isoproterenol binds to the 7 transmembrane beta-1 receptors located on the surface of SV nodal cells. The beta-1 receptor is coupled to a stimulatory G protein composed of 3 subunits, meaning that upon binding of isoproterenol, the G-alpha subunit will dissociate from the regulatory beta-gamma complex and activate the enzyme adenylate cyclase located on the intracellular membrane. Adenylate cyclase then catalyzes the conversion of ATP to 3'-5' cyclic AMP. First, cyclic AMP can bind to a small CAMP pocket located on the IF channel itself and increase the cell's permeability to sodium. By directly increasing the permeability of sodium via the IF channel, phase 4 slope is increased, the autorhythmic action potential is able to occur quicker, and more action potentials can occur within a given amount of time. Increase heart rate. An increase in cyclic AMP activates protein kinase A, which can then phosphorylate LTCC, enabling the channels to work better, lowering the threshold needed to fire an action potential, and also allowing more action potentials to occur within a given time. Isoproterenol also binds beta-1 receptors on AV nodal cells and increases conduction across the AV node by the same mechanism. Wow, I think my contractions are getting stronger too. We can also look at the physiology behind your contractions, Pat. The increase in SCA is a result of isoproterenol binding beta-1 receptors on contractile cells, responsible for affecting inotropic state and the duration of contraction. Muscle contraction is associated with the binding of calcium to troponin. Therefore, controlling calcium controls the degree of contractility. When isoproterenol binds to the beta-1 receptor on contractile cells, just as before, the alpha subunit activates adenylate cyclase. ATP goes to cyclic AMP. Cyclic AMP activates protein kinase A, pKa, which once again goes on to phosphorylate other things. pKa can phosphorylate LTCC on the basolateral membrane, which increases the permeability of calcium. pKa phosphorylates phospholambam, which prevents it from inhibiting SERCA2, a calcium ATPase on the SR. Finally, pKa can phosphorylate type 2 ryanodine receptor calcium release channels, or RYR2. The increased permeability of calcium due to enhanced SERCA2 and LTCC speeds up removal of calcium from the cytosol. This shortens the time calcium is bound to troponin and decreases the active time of the myosin cross bridges.
I'm taking this magical chemical home with me. That looked like a pretty crazy trip. Give me some of that caffeine.
Have fun, kid.
Woo! What's happening? Is this speeding up my heart rate too?
Yes, little Patty. Caffeine affects SV nodal cells through the same GS pathway as isoproterenol, though not directly. Normally, the enzyme phosphodiesterase slows or stops the effects of the GS pathway by converting CAMP molecules back into AMP, a molecule no longer able to activate pKa or LTCCs. When caffeine is added, however, it acts as a competitive phosphodiesterase inhibitor, so less CAMP molecules are converted back to AMP. The net result is an elongation of the effects of CAMP, greater activation of pKa leading to greater LTCC activity, and an increase in conductions through funny channels. This manifests as an increased heart rate and an increased conduction through the AV node.
I think my contractions are getting bigger.
That can also be explained by some physiology, Patty. Caffeine is a positive inotropic agent, meaning it leads to stronger contractions. This is yet again due to its inhibition of phosphodiesterase. Usually, CAMP acts with the contractile cell by activating pKa, which in turn phosphorylates LTCCs and phospholambam. This results in increased calcium conductance both into the cytoplasm and into the sarcoplasmic reticulum. This increase in intracellular calcium stores leads to greater binding of troponin and more actin-myosin cross-bridges. With caffeine, levels of CAMP are increased, causing an increase in the magnitude of its effects. This culminates in greater myosin-actin binding, more power strokes, and stronger contractions.
I'm digging this caffeine.
I'm not letting you guys have all the fun. Give me that potassium.
Okay, but just one bite.
Nom nom nom.
No, kid, just one bite. I said just one. You must have had 8 doses. You're on your own now.
I don't feel so good.
Poor Patrick. He really should have looked at the data. Within cardiac cells, action potentials depend on the flow of ions across the membrane of the cell. The flow of these ions is contingent upon the electrochemical gradient of each ion. The equilibrium potential for individual ions can be determined by the Nernst equation, and the membrane potential can be determined by the Goldman equation if there are multiple ions involved. In contractile cells, the resting membrane potential in phase 4 is determined primarily by the flow of potassium through leak channels, making the value negative 90 millivolts. When an action potential arrives, the membrane is depolarized and voltage-gated sodium channels are activated. These channels allow conductance of sodium until they are inactivated. Normally, these channels deactivate upon the complete repolarization of the membrane, allowing the cell to elicit another action potential upon the addition of extracellular potassium. However, the electrochemical gradient of potassium is changed, and the resting membrane potential changes to a less negative value. This has large consequences for the development of action potentials. This film was made in memory of young Patrick. His death inspired our experiment to quantify the effects of these drugs on frog hearts.
Our methods were similar to the frog ECG lab conducted earlier this quarter. This is a diagram of our setup showing the isotonic transducer and connections to the power lab. The isotonic transducer was calibrated and a linear regression was used to derive the calibration equation seen here. Ideally, a recorded ECG wave shows an SVP wave signifying depolarization of the sinus venosus and right atrium, a QRS wave signifying ventricular depolarization, and a T wave for the ventricular repolarization. Usually, the PR interval was measured to determine the time period for atrial depolarization and conduction across the AV node. The QT interval was also measured to determine the length of ventricular depolarization. In this experiment, these intervals were modified slightly, as seen in the diagram on the right, due to the lack of distinction between the T wave and the SVP complex. Separately, the RR interval was measured to determine heart rate, and the systolic contraction amplitude was measured to compare contractility.
The increased heart rate of 9% can be attributed to isoproterenol binding beta-1 receptors on SV nodal cells and accounts for isoproterenol's positive chronotropic effect. The fact that heart rate increased, a decreased RR interval, can be seen by the decreased MQT interval observed. Maximizing the rate of phase 0 depolarization by binding beta-1 receptors on AV nodal cells resulted in an increase in conduction velocity across the AV node, seen as a 7% decrease in the PR interval, and accounts for isoproterenol's positive dromotropic effect. The positive inotropic effect observed, the 13% increase in SEA, is due to isoproterenol binding beta-1 receptors on atrial and ventricular contractile cells.
This table shows the effect of caffeine on heart rate, systolic contraction amplitude, modified PR, and modified QT intervals. Compared to the control, 3 pipettes of 1 millimolar caffeine solution increased the heart rate by 7%, the SCA by 22%, and decreased the modified PR interval by 5%, and the modified QT interval by 2%. These results can be explained by the physiological mechanisms discussed earlier. It is important to understand caffeine's effects on cardiac cells because it is found in many beverages and foods and is the most widely used psychoactive drug in the world.
This table summarizes the results obtained after 8 doses of 1 pipette full of 1 molar potassium solution were added. For the control, the heart rate, modified PR, modified QT, and SCA were measured, but these same parameters could not be measured post-application of potassium because all heart activity ceased. This cessation of activity is presumed to be due to the physiological mechanism discussed earlier. Potassium solution is an interesting substance due to its various and sometimes sinister applications. Medically, it is used to induce elective cardiac arrest during heart surgery, allowing surgeons to work efficiently. Conversely, it is also used within the cocktail of drugs within a lethal injection used in the criminal justice system. In conclusion, frog cardiac tissue has a high degree of homology to the mammalian heart. Both have cardiac cells that contain beta-1 receptors corresponding to GS transduction pathways, both utilize CAMP to increase activity, and both depend on the maintenance of specific ion concentrations across the membrane for proper functioning.